The space segment of GPS consists of a constellation of satellites orbiting the Earth. These satellites are arranged in 6 orbital planes, with at least 4 satellites in each plane to ensure global coverage. The GPS system requires a minimum of 24 active satellites to provide global coverage, though the current constellation typically includes 31 operational satellites. Each satellite orbits at an altitude of approximately 20,200 kilometers above Earth's surface and completes 2 full orbits every day. These satellites continuously transmit radio signals containing their precise position and the exact time the signal was sent. The signals include data about the satellite's position and precise time information, which GPS receivers use to calculate distance from each satellite. These satellites are constantly monitored and maintained by ground stations to ensure accuracy and reliability. Regular adjustments correct orbital positions and atomic clock errors. With an average lifespan of 7 to 12 years, GPS satellites are regularly replaced to maintain the health of the constellation and ensure continuous global positioning services. The control segment forms the backbone of the GPS system, consisting of a global network of ground stations. At the heart of this network is the Master Control Station in Colorado Springs, which coordinates with monitor stations worldwide. These stations continuously track the GPS satellites and communicate with them, sending and receiving critical data. The control segment performs 4 key functions that are essential to GPS operation. First, it tracks and monitors satellites, ensuring they remain operational and detecting any anomalies. Second, it maintains precise satellite orbits, making adjustments as needed to keep them in their designated positions. Third, it synchronizes the atomic clocks on board the satellites, which is critical for accurate timing and positioning. Finally, it uploads updated navigational data to the satellites, which is then transmitted to GPS receivers worldwide. The Master Control Station is the nerve center of the entire GPS system. Operated by the U.S. Space Force in Colorado Springs, it runs 24/7, coordinating the entire network and computing orbital data that ensures GPS accuracy. Without the control segment, GPS satellites would drift from their orbits, their clocks would lose synchronization, and the entire system would gradually degrade, making this behind-the-scenes network critical to GPS reliability. Trilateration is the mathematical method GPS uses to determine your position on Earth. Let's start by understanding the concept in 2 dimensions. Imagine each satellite broadcasts a signal that travels at the speed of light. Your GPS receiver measures how long it takes for that signal to arrive. By knowing the speed of light, the receiver calculates the distance to each satellite. Each distance measurement forms a circle centered on the satellite. With 2 satellites, your position could be at either of the 2 points where these circles intersect. To resolve this ambiguity, we need a 3rd satellite. In 3-dimensional space, the principle is similar, but instead of circles, each satellite defines a sphere. In 3 dimensions, we need at least 3 satellites to determine a position. The intersection of 3 spheres results in 2 points. Usually, one point is far from Earth's surface and can be discarded. However, our GPS calculations rely on precise timing. Even tiny timing errors can lead to significant positioning errors. This is why we need a 4th satellite. It provides an additional equation that allows the receiver to solve for time, eliminating timing errors. Let's summarize why 4 satellites are necessary for accurate GPS positioning. 3 satellites can determine your position in 3-dimensional space through the intersection of their distant spheres. The 4th satellite is crucial for correcting timing errors between the satellite's atomic clock and your receiver's clock. Timing is extremely important because light travels at 300,000 kilometers per second. Just 1 microsecond of timing error would result in a 300-meter position error. And that's how GPS uses trilateration with 4 or more satellites to accurately determine your position on Earth. Global Positioning System provides remarkable precision in determining your location. According to NASA's performance standards, GPS can pinpoint a position with 95% confidence levels of approximately 10 meters horizontally and 20 meters vertically. This means that 95% of the time, your horizontal position will be accurate within a 10-meter radius of your true location. Vertical accuracy is typically less precise, with a standard of about 20 meters from your true elevation. GPS also provides remarkable time precision, accurate to within 10 nanoseconds. This temporal accuracy is crucial for many applications requiring precise timing. Several factors can affect GPS accuracy. Let's examine the most significant ones. Satellite geometry, or geometric dilution of precision, significantly impacts accuracy. When satellites are well distributed in the sky, position calculations are more precise. Poor satellite geometry occurs when satellites are clustered together, resulting in less accurate position calculations. GPS accuracy has improved dramatically over the decades due to technological advancements and system modernization. In the early 1990s, civilian GPS accuracy was intentionally degraded to about 100 meters. By the early 2000s, this restriction was removed, improving accuracy to around 30 meters. Modern technological advances, including better satellite design, improved ground control, and enhanced receiver algorithms, have further increased accuracy to about 5 meters today for consumer devices. Continuous advances in GPS technology, including new satellite generations and integration with other systems, are expected to further improve accuracy in the coming years. These improvements will enable more precise applications in areas like autonomous driving, precision agriculture, and location-based services. GPS technology plays a critical role in autonomous vehicles, providing the precise positioning information needed for navigation and safety. Autonomous vehicles rely on GPS for centimeter-level positioning accuracy, which is essential for safe navigation on roads. The GPS system provides real-time data that helps vehicles determine their exact position, optimize routes, and adapt to changing traffic conditions. For full autonomy, GPS data must be integrated with other sensors like cameras, LiDAR, and radar to create a comprehensive understanding of the vehicle's surroundings. Beyond autonomous vehicles, GPS technology has been miniaturized and integrated into a wide range of wearable devices. Smartwatches and fitness trackers use GPS technology to track location, record workout routes, and provide accurate metrics on distance, pace, and elevation changes. These wearable devices offer valuable features like fitness tracking, personalized route mapping, and safety alerts, all powered by integrated GPS technology. The remarkable evolution of GPS technology has been driven by continuous miniaturization of receivers. From bulky handheld devices in the 1990s to tiny microchips today, GPS receivers have dramatically reduced in size while improving in performance. This miniaturization has made it possible to integrate GPS into increasingly smaller wearable devices, while also improving battery life and reducing production costs. GPS technology has transformed numerous industries with its precise positioning capabilities. In fleet management, GPS enables route optimization, real-time tracking, and enhanced security. In agriculture, GPS-enabled tractors perform precision seeding, watering, and fertilizer application, reducing waste and improving yields significantly. GPS tracking is vital for asset recovery, helping locate stolen vehicles and equipment with impressive success rates. Environmental researchers use GPS to track wildlife, monitor habitats, and gather crucial data for conservation efforts. Construction companies rely on GPS for digital blueprints, precise excavation, and even aligning tunnels begun from opposite sides of mountains. In public safety, GPS guides emergency vehicles along optimal routes, drastically reducing response times and helping save lives.